Hi guys, so we are all aware of the structure of DNA. It's a double helix made up of four kinds of deoxyribonucleotides called adenine, guanine, cytosine, and thymine, has a sugar phosphate backbone, and an anti-parallel arrangement. Well, this video will focus on replication of this double-stranded DNA molecule. What you also see on the screen are the components of replication that are essential to the process of replication. What I'm going to do is, as I'm going to talk about these important enzymes and proteins, I'm going to mark them off my list. Makes the process a little bit easier. So let's start the replication. Replication starts off by binding of initiation protein to the double-stranded DNA molecule. So this is my initiation protein that binds to the double-stranded DNA molecule. What it does is that it creates something called a replication bubble, a few nucleotides down the line. So something like this. My initiation protein is still here. And this is my replication bubble. How does it do that? Replication bubble is basically a region rich in adenines and thymines. Recall, adenine and thymines are attached to one another through 2 hydrogen bonds versus the 3 hydrogen bonds. So they're a little easier to melt. What initiation protein along with some ATP does is that it melts those hydrogen bonds and creates this replication bubble. Another important thing to note about prokaryotic replication is that it's bidirectional. It proceeds in this direction and in this direction. What I'm going to do is that I'm going to show what happens in this direction. Something like this. But keep in mind that the events that are happening in this direction, in the right direction, are the exact same events that are happening in this direction. The same enzymes are involved. So the function of the replication bubble is to attract an enzyme called DNA helicase. Helicase recognizes this replication bubble and comes and binds to it. The function of helicase is that it makes the replication bubble bigger by unwinding the DNA as it moves down the DNA molecule. The function of helicase is analogous to how the zipper on your backpack works. You open the zipper and voila, your backpack opens. Another enzyme called gyrase goes ahead of helicase to remove the supercoils that are introduced by helicase as a result of its activity. At this point, consider your DNA like a rubber band. So this is my rubber band here. I twist one end of my rubber band and it becomes something like this. I keep twisting that end. It gets messier and messier every time. This is what is happening right now as helicase is continuing its unwinding activity. Down the line, supercoils are being introduced. That, if encountered by a helicase, will dramatically slow down its speed and the rate of replication. Gyrase is the enzyme that makes sure that these negative supercoils are untangled so that a helicase can continue unwinding the DNA at a normal speed. That's what gyrase does. So I have my initiation protein, helicase, and gyrase. Another enzyme called single-stranded binding proteins bind to my template strands and makes sure that these strands do not reanneal back together. These two strands are complementary, and the first chance they get, they're going to go reanneal back together. The single-stranded binding proteins make sure that they don't. So they serve a very important function. That is my initiation complex. So that's my initiation complex right there. The next step is my elongation. Elongation of new strands starts off by short RNA sequences called primers. A lot of people question the importance of primers. There is a concern in DNA replication. The major concern is that the DNA Pol 3, the enzyme that adds nucleotides to the newly synthesized strand, it cannot start from scratch. It only adds adds to an existing 3' hydroxyl group. That 3' hydroxyl group is provided by these primers, by these short stretches of RNA nucleotides. That's the function of primers. So once I have my primers in line, DNA pol can come in, bind to my primers, and start synthesizing new strands. So this is my DNA pol 3. DNA pol 3. And start synthesizing my newly synthesized strands by adding nucleotides. The synthesis of new DNA strand is always from 5' to 3'. 5' to 3'. Now there is a problem. This strand going from 5' to 3' in the direction of replication fork just follows helicase, everything is unicorns, hunky-dory, strand goes perfectly. This strand that goes in the opposite direction of replication fork faces some trouble. This strand is synthesized in fragments called Okazaki fragments. This strand is called leading strand, and that strand is called lagging strand. So this is one fragment. This right here is another. My primer, my DNA polymerase, and then my nucleotides going 5' to 3'. What then happens is after the synthesis of the new strands is done, another enzyme called DNA pol 1 comes in and degrades the primers and replaces it with the nucleotides. So this goes, and we have this. DNA pol goes too. We don't need pol 3 no more after my synthesis is done. Instead we have nucleotides. So we have one strand going from 5' to 3', a new completely synthesized strand. But look at this on this strand. We have a 5' to 3' and a 5' to 3'. We have two different strands. Each fragment, as said before, is an Okazaki fragment. So what should happen? We need another enzyme called DNA ligase to literally glue them back together so that it looks like one strand, just like this one does. So ligase comes in and glues them back together. This is my ligase, my DNA ligase. So my primers, pol 3, deoxyribonucleotides, pol 1, and my ligase. So every good thing comes to an end, and so does my replication. So how does replication end in prokaryotes? A termination protein called TUS protein binds to termination sequences and blocks the movement of helicase, preventing the replication fork from advancing and terminating the replication altogether. So it inhibits the activity of helicase. No helicase means no synthesis of new strands because no template strands are being unwinded. So you don't get no unwinding strands, you don't get no new strands. So that's pretty much it. Replication is initiation, elongation, and termination. That's it.